First of all, thanks a lot for letting me speak and present the non-relativistic story behind the large charge expansion. And I also want to thank Gabriele for making my presentation much easier to introduce and much more exciting, because I'm going to overlap a little bit with the things he said. And for this, I will recap very quickly some of the things he presented, and which are the very basic notions we have to bear in mind as we go through the non-relativistic story. If we want to study the state operator correspondence, if you want to, we are going to use the state operator correspondence if we want to study the conformal dimension of the lowest operator of charge Q. And this amounts to building the superfluid effective theory for the goldstone on the cylinder. And this theory has a well-defined separation of scales, right? One scale is, roughly speaking, given by the volume of the sphere in which you map the theory, and the other scale is given by the chemical potential that comes from the VEF of the goldstone, right? And this separation of scales guarantees that the derivative expansion of the EFT is controlled by the inverse powers of mu, which amounts to inverse powers of Q in the following form. So this is a suppression factor that we get in the relativistic case. And bear in mind that I work in D+1 dimensions, so this is a little bit confusing, I guess, depending on which notation you use. The first line here is actually pretty simple to obtain, right? You write down the effective action, and then you just evaluate the VEF of all the operators in the superfluid ground state. But on top of that, you might want to include quantum corrections, right? And if we do energy, which amounts to computing the determinant of the fluctuations above the ground state, right? And so for this, you need the spectrum, right? And the multiplicity of the eigenvalues on the sphere, and then you just sum and you try to make sense of this expression. Okay. And so as an example, I just recap the most famous examples, right? The d = 2 and d = 3. So 2 + 1 and 3 + 1, right? Dimensions. And when d is even, we expect, as Gabriele said before, there is no classical term to renormalize the quantum fluctuations to leading order. So we expect this thing to be universal, and it is, right? There is no Wilsonian coefficient entering this term here. And he also showed very nicely last year that we get also a universal term in this expansion in the form of a log Q term in odd dimensions. And this will be important because the same thing happens in the non-relativistic story, which I will present. And so what does it look like? So by the way, when I say non-relativistic, I mean, I just use the most naive definition of non-relativistic scale invariance, which means that the time coordinate scales twice as much as the spatial coordinates, right? It's the symmetry group of the free Schrödinger particle, right? That's why we call it the Schrödinger symmetry. And so the expansion takes the exact same form to start with as the relativistic case, namely an expansion like this, right? But then we have extra structure, which is, I guess, very interesting. And I will comment on that, and I will try to convince you that this expression is actually the one we have to use. And this expression does not contain quantum corrections yet, right? So this is the classical part of the expansion, which is much richer than the relativistic case. And in particular, keep in mind this suppression factor here, that is the cubic root, and I will refer to it later on as the delta. It's just a name that I give it, and I will refer to it in a moment. So there is a more defined expansion in the non-relativistic case. And of course, I will then try to compute the universal contribution as energy. And as an example, I also wrote down here the d equals 2 and d equals 3 case, where you have new terms, right? And I basically forgot to tell you that these terms here, the b's, b1, etc., they may contain log q terms when d is even, right? And these terms are not universal in the sense that they come with a Wilsonian coefficient. And this I will discuss in detail in the following. So you see, you have this surprising term here, this one, and then a universal prediction, just like in the relativistic case. And the d equals 3 expansion, well, d equals 3 case is much richer than what you would expect in the relativistic case. And I will also try to explain where this thing comes from. It's exactly the same reasoning as the relativistic case. Okay, and so the setup that I will be using here is, well, I will implement the state operator correspondence in the non-relativistic case. But for this, I have to couple the theory to a harmonic trap, an external harmonic trap, which, as you can guess, is quite different from just moving to the cylinder, right? And the way to implement that is to consider the harmonic trap as sort of a gauge field that couples to the time derivative. So this was, well, you can see that from the coset construction, if you like, in the coset. Otherwise, you can also argue from the general coordinate invariance that Son and Wingate developed a couple of years ago. And what you have to bear in mind is that the building block takes the following form, right? So, of course, in the non-relativistic case, you have to have only one time derivative and two spatial derivatives. So that's why it takes the following form, right? And as I said, the harmonic potential takes the form of a sort of a gauge field, right? With respect to the time derivative. Bear in mind that I turned off all the constant for simplicity. And so the leading order action here should be thought of as what you would have gotten in the relativistic case, right? It's just the leading order kinetic term of the nonlinear sigma model. So it's the equivalent, but now I'm going to have to implement the correspondence through this coupling here. And then I put the theory in the superfluid ground state, right? So the Goldstone mode guy acquires a VEF, that is the chemical potential times time. And then you can simply evaluate the VEF of this object here, and you just get mu and the harmonic potential. And here I will introduce a new coordinate, spherically symmetric coordinate Z, that takes the following form here, and you will soon realize that it's extremely convenient to express everything in terms of this Z coordinate. And I'll also introduce something that I don't tell the name yet. It's just a radius that goes, oh, there is a square root here. It goes like square root 2 mu, and I'll explain in a second what it is. So you can write down Z as being the ratio of R squared over R squared. In order to make sense of this parameter, we can have a look at the ground state charge density. And I should also mention that the charge density in the non-relativistic case corresponds to the particle density, right? The U1 symmetry embedded in the Schrödinger group is actually the particle number, the number of particles, basically, right? So the charge density in the ground state takes the very simple form U times Z to the power 0.2. So there is a point in space, well, like a set of points in space that correspond to Z is equal to 0, where the charge density vanishes. And so what is this point? It's just when R is equal to my finite R here, right? And this means that classically the particles cannot spread out of this volume, which is a spherical cloud, classically, right? So this is why I called it the radius of the cloud. And so, well, this is how we implement the state operator correspondence. And then, I mean, we can just proceed and try to see how the leading order term in the conformal dimension goes about, right? And this just amounts to computing the ground state energy, right? So you just try to relate first mu to q, which is exactly the same as in the relativistic case, where zeta is just a constant, right? And then you integrate the ground state energy density over the volume of the cloud, and you get the following expression here. Right? So this is how our expansion starts. And now we want to include subleading corrections to this expression here. But first, I want to comment on my change of coordinate, right, which is quite unusual. So I recall it here. This is the change of coordinate I perform whenever I'm in the ground state, because the ground state is spherically symmetric. So this coordinate is very convenient for all my purposes. And so one comment I want to do is that to mention the fact that as we include more and more derivatives, we suppress more and more the contribution in the end, right? Roughly speaking, it just means that my EFT also has a well-defined separation of scales, which controls the expansion. And so I expect to have sort of the same results as in the relativistic case. Yet another comment is that, as I said, the support of the theory now is confined to a cloud, a spherical cloud, right? And whenever I integrate a quantity over this volume, I can turn it into an integration from 0 to 1. Well, my z is actually 0 on the boundary and 1 in the center. So any integration over the whole cloud is turned into an integration from 0 to 1, and then I get just some prefactors. And an important thing to notice is that the volume of the cloud goes like mu to the power d over 2, which is just, our cloud to the power d. And so it means that it's quite easy to understand that the cloud will expand more if we include more stuff inside, right? So this is very different from the relativistic correspondence, where we put the theory on a finite Q-independent sphere, right? So here it's quite different. And once I do that, then I can discuss how to include more operators in my theory. And actually, there is not much choice. I have my operator u. I can take derivatives of q. The only one I need to consider on top of that is z, capital Z, which is also dictated by general coordinate invariance. It's the only operator that I need to consider. Otherwise, all the other ones have just a vanishing VEF, and so I don't consider them, right? And even more so, you have to think of u as the dressing operator. You can also regard it as it's the one that adapts its exponent, its power, in such a way that the operator gets marginal. You can also see that from the coset construction, where the Einbein allows for, through the determinant of the Einbein, you get an invariant measure. And this is just the power of u. And it's also it's the same as saying that you integrate the radial node out. So this u is the one that adjusts its power here in such a way that the whole thing is marginal. And okay, so this is the most general sort of operator I can have in the bulk of the cloud. I'm not trying to approach too much the boundary of the clouds because things get divergent. So for now, I just address operators in the bulk. And so you plug everything you know about them, right? So I know how to evaluate the derivative with my law here, and I know how everything behaves, right? So I just collect factors of mu, of z, of 1 minus z, right? And I have an expression like this for the contribution of this operator to the charge, to the conformal dimension. Okay. And so, the goal is to evaluate and analyze a little bit the behavior of this integral here. So one very physically motivated procedure would be to replace the lower bound of this integral by delta whenever the integral is expected to diverge. And it so happens when m and n are too big, right? If this thing is too negative, then the integral will not converge. So you might replace the lower bound by delta. The delta is this factor that I introduced before, and you can regulate the theory in this way, which is exactly the same as what Cuomo was saying, where you say that your effective theory is expected to break down as you approach the boundary, so you cut it off. You just cut off, right? Replacing 0 by delta amounts to saying that I just throw away the outer part of the cloud of particles, right? Yet a more simpler way, a more simple way of evaluating the behavior of this integral is to use the capital beta function, right? The one from the mathematicians. So because we have 1 minus z and z to some powers, right? So I can just replace this by a bunch of gamma functions as such. Okay, and now I will comment on what happens in this case. So I have this expression that I need to analyze because, well, I just throw away functions that will not cause any trouble, and I focus on this one. So it can either be finite, right? So it's just a number, and then you just see what happens, right? You have an expansion that starts at mu to the d plus 1, and then you decrease by multiples of 2. And this is the standard expansion that also holds in the relativistic case. And in particular, when d is odd, you will hit q0 at some point, right? Because, this condition can be satisfied. This being equal to 0 can be satisfied when d is odd, and so you have q0 terms. And this actually tells you that you should expect a pole in the Casimir energy, and you will have to use this operator to renormalize the theory of the Casimir energy at some point. Okay. Yet another very interesting thing that can happen is when, well, this thing is 0 or even a negative integer. But let me focus on the case where it's equal to 0. So I satisfy this condition, which can only be true when d is even, right? In which case I end up with gamma 0, and I have a pole. So I move to dim-reg, where I just shift the dimension by 2 epsilon, and I expand as you would do in CFT1, right? So you get this this expression here. This is telling you something very nice, I think, right? We have power of mu, which is a power of q, essentially. It's this one, right? And a log. So we have our classical non-universal logs arising from this analysis here. And you can also recover this result by using the delta regularization that I mentioned before. And something very important to deal with now is this 1 over epsilon, right? Because you have to get rid of this pole somehow. And it was clarified last year by Simeon and, well, Helleman and Swanson, I should say, how to treat this divergence. And they proposed the following construction. Whenever the particle density is, you place counterterms that, well, basically will serve as counterterms to renormalize this divergence here. And the construction goes as follows. You put a delta function that has well, basically the particle density inside of it, which means that the counterterms are really localized where the particle density vanishes. And then you dress the operators as well, basically with all you can. And this I clarified in my recent paper. And the only edge counterterms you can have has the following form. So it's z to some power, and then you use dressing operator. And you have noticed, I guess, that this is not the same dressing operator as before, because before we were using u, which vanishes. So I have to use another dressing operator, and this is the one we have to use. So once you build such a counterterm at the edge of the cloud, you can evaluate how it contributes to the conformal dimension. And it contributes exactly as you need it, in the sense that it contributes in the following way. And if you remember well, this is exactly what we had before with the pole. We can renormalize the coefficient that goes in front of this operator here in such a way that the pole cancels. And this also triggers the whole expansion that started at 2n minus 1 over 3d with the suppression factor 2 over 3d, right? So to summarize, we have the following expansion so far. We have that, and this is in terms of mu. And if you want to express this in terms of Q, the charge, right, you have, of course, to replace, but it's not enough to just care about the leading order behavior, because then something might happen with corrections. And this is what happens here, where this, well, basically this behavior here generates yet a third structure here. So that's why we have 3 lines in the expansion of the delta Q. But I guess the most important thing to notice is that we have, oh, I guess, so here there is a 3, I should add 3, right? So there is a more refined expansion in the non-relativistic case. And on top of that, we have logs sometimes hiding in the B's here. Okay. So I guess I should ask if there are questions so far. Okay, so I will quickly comment on something that Gabriele mentioned, which is basically experiments, right? But here the connection is much stronger than in the relativistic case, because the correspondence actually maps, well, the theory, the non-relativistic CFT in flat space to something that they actually measure in the lab, like literally in the lab, right? So because people have been trapping particles in harmonic traps for decades, essentially. So even before we knew about the correspondence, right? So this is quite interesting that we have such a strong link between well, the energy spectrum of that people have been measuring in the lab and things that we compute. And a very, oh, can you see? Oh, okay, there is a missing slide. Okay, I wanted to talk about the BCS, Bose-Einstein condensate crossover, where the picture is not super relevant, so it's not important. But what you have to bear in mind is that people in the lab are able to trap a fermionic gas and tune the interaction parameter. And so they can go from the Bose-Einstein condensate regime of the Fermi gas to the Cooper, well, the BCS regime on the other side. And right in the middle of this thing, there is a point where the system has an emergent scaling variance in the non-relativistic sense. So this point, exactly this point, we would call it the conformal point, in the sense that this is exactly what I've been describing so far. So then the question arises of whether we can move away from the conformal point and somehow reach the Bose-Einstein condensate side or the BCS side somehow, using like very theoretical tools. And the hint in this direction, I guess, is the following: when there is a large number of trapped particles, it is known from the cold atom community that the expansion of the ground state energy takes the following form. And so it looks a lot like the things we obtain in at the unitary point, right? The point where things are scaling variant. And the question is, can we explain these better, or can we bring some new corrections? So can we bring some better understanding of what is going on using what we know about the conformal point? And can we do the same on the BCS side, for instance? So that would be very exciting and very much related to what people do in the lab. So this is as close as it gets to experiments, right? Okay, but anyway, so let me go back quickly to the computation of the Casimir energy that we have recently done with Domenico, Ian, and Susan. So the Casimir energy is just the sum over over the eigenvalues times their multiplicity on the sphere, right? And then, well, the square root is not super convenient to handle. So if you want to recover so I'm after a zeta function here, right? So I will replace the square root by this factor minus s, and then use the binomial expansion essentially 4 times in a row to expand this thing here and this thing as well. And in the end, I get a pretty big expression, but the upshot is that we recover some not some well-known, but some known zeta function that mathematicians have studied in the literature. So you have to get to find that, right? Luckily, Domenico did, and so we recover the model Thornheim zeta function, which is I guess not super famous, but anyway. And so we actually know there is a recipe to extract the poles of this zeta function, and there are conditions you have to impose on S1, S2, and S3 to extract basically the residue at the pole. The condition that is relevant in our case is S1 plus S2 plus S3 is equal to 2. So you solve this, you plug it back here, you compute the prefactor, and well, we obtain the following expression for the pole. So this is very nice, but so this is exactly the thing that we want to get rid of, right? By renormalizing the Casimir energy, and for this we need a counterterm. The appropriate counterterm, I've already told you what it looks like, right? We just have to look for a term that scales like Q0 in the end, right? And this is satisfied in d equals 3 by this condition here, and then you move to dimreg, so you actually don't have mu to the 0, but you have mu to the minus 2 epsilon, and you expand, and then you want to cancel the pole in the Casimir energy, right? I'm extracting the residue, and then I want the residue to cancel out in this expression, which means that the Wilson coefficient that I put in front of my operator has to get renormalized, and it gets renormalized in the following way, right? And so if you do so, then well, I mean, you have to then plug this back in this expression here, and you see that this epsilon here multiplied by this 1 over epsilon here cancels out, and you end up with a finite universal log mu or log q term of this form here. So this essentially completes what I wanted to say. So let me summarize. The classical part of the expansion of the conformal dimension in the non-relativistic case takes the following form, which is much richer than the relativistic case. And you actually have, on top of that, logs sometimes hiding in the B's here. And typically you have the expansion that I showed at the beginning for d equals 2, and the same for d equals 3. So, the very recent result that we got is the computation of this term with and many comments. As a quick look at the future directions of research, I can mention that Kravek and Pal have studied the same story, but with a spin, which is very reminiscent from what Gabriele presented today. And we could also imagine like improving this analysis in the light of the counterterms that Simeon and Ian found last year. There is also some work on the gravity duals of these theories, and it will be interesting to investigate the consequences of this work on the gravity side. Again, I come back to the BCS Bose-Einstein condensate side, which I've unfortunately I was not able to show the picture, but I really think that a full description of the BCS back over is a Nobel Prize winning question. So I think it's worth trying at least. And then people have also tried to go to non-abelian case where the U1 symmetry is replaced by a spin N symmetry to the large N limit, and perhaps we can imagine doing like the resurgence program that was performed in the relativistic case last year, We could also include party violating terms in T+1, for instance, as was done in the relativistic case this year as well. And yeah, that's already quite a few directions. So, thanks a lot.